Good afternoon, everyone. Thank you very much for joining this Using Additive Manufacturing to Shape the Future webinar. Thank you all for attending. For those who already haven't, if you want to open the chat box, you can do that via, if you move your cursor onto the screen, you'll see a number of buttons appear at the bottom. There's a blue button with a speech bubble in it. If you click on that, that will then open the speech box. The chat box. You can then basically chat to everyone in there. You make sure all participants is selected from the two buttons, drop down menu. Then what you can do then is select there. And if you can then introduce yourself as you go along. If you have any questions, please put them in the chat box. We'll come to them at the end of the session and look at them. We'll try and group them together in the relevant topics. We've got quite a lot of content to get through, so what I'll do is I will welcome everyone. Matthew is going to be delivering the presentation. I'm Rob Osingooder, I'm the moderator. And what I'll do now, I'll hand you straight over to Matthew to carry on with the content. Thank you, Matthew, over to you.
Thanks very much, Rob. Just checking that you can hear me okay. Rob, just check, can you hear me all right? Yep, good. Okay, thank you very much, Rob. It's great to have everyone's company for the next hour or so.
Hello, Matthew. You're on mute at the moment. We can't hear you.
Mute. Should be okay now. Rob, everyone. I'm getting lots of yeses loud and clear, Rob, so I think everyone else can seem to hear me. I'll keep going then. Good. So yeah, as Rob said, my name's Matthew Laskay. I deliver a wide range of training courses for the Institution of Mechanical Engineers around the country, and I'm also involved in other divisions of the IMechE. So I'm the chair of the Aberdeen area in Scotland, where I'm currently living. Outside of this, I manage my own engineering consultancy called Project Engineering Management Limited. So we manage engineering projects and provide training services. So we've got a background in mechanical engineering, but also in industrial design. So I'm really excited by the development that 3D technology is bringing, and also the possibilities for the future. And that's the whole purpose of this webinar. It's what are the possibilities for the future that a 3D manufacturing can bring. So let's go back a little bit first. When I was young, I loved Lego. I loved playing with it hours and hours. I loved all of the different kits you could buy. This spaceship that you can see on the screen there was my favorite one. We had loads of different kits which we'd mix all together to make weird and wonderful designs. We had spaceships mixing with the knights and the racing cars. And at the time, I thought it was pretty creative, pretty wild what we could do there. But I would never have thought that it could turn into something today like some of these Lego, the International Space Station here. So when I look now at what 3D printing can build, or additive manufacturing as we call it, I think back to sort of where these Lego days started from, and there's a lot of similarities between building Lego back when I was a kid to what 3D printing can bring now. It doesn't have to be much more complicated than this, but it clearly can. So for example, here's a 3D model which I've imported from a program called Tinkercad. That little spaceman there on the left can be printed in 3D in a 3D printer. Then with the click of a button, I can convert that into Lego and print that version instead. Or if I really wanted to, I can completely design a whole new Lego man. So here's an example of a Lego spaceman that somebody's designed, pending on copyright, of course, and you can print that instead. So really, your imagination is the limit, and it doesn't have to be too complicated, but you can make it as complicated as you want it to be. So this is what I want you to get out of today's session. This is the purpose of what I'm wanting to talk about. The different additive manufacturing processes, the different design possibilities that it can bring. it can increase your efficiency and your profitability in your workplace. But I also want you to show how you can sort of get started designing and printing your own parts with not too much knowledge. So we're looking at both the workplace and at your home and how that's going to be used for future. So first off, I want to start briefly about the design process, because the design process when we're thinking about different manufacturing techniques are slightly different. About a year ago, my pistons decided to smash into the valves on my car. So this is what the inside of my engine looks like after I had to pull it all apart. The 4 cylinders and the 4 pistons there showing on the left. At the bottom of this piston is what you call the crankshaft, which is shown on the top right of the screen. Typically, they're made using traditional processes like casting or forming or machining, which I'm going to talk a little bit about soon. But thanks to advances in additive manufacturing, we've now got other options we can consider, more efficient options to design it, to look at the loads, to look at material properties, and to look at what other ways we can do it. So here in the middle of the screen, we've got a 3D printed crankshaft. You can see it's not the same one. I don't have a Honda, but it's very similar style, but it's made a lot more efficient. It's got all of the parts in the place where you want them. Or you can get a little bit more complicated and you can design a whole engine block like the one on the right there that's being 3D printed. It's not just as simple as taking your existing crankshaft, converting that into a file and printing on a 3D printer. We need to sort of go back a step through the design process and look at what's going to be affected and where can we optimize these designs. So as an example, take this crankshaft from a ship. It's the largest reciprocating engine in the world. 300 ton, each piston weighs about 5.5 ton. This is a bit more of a challenge than the one from my car. Bigger, heavier, and more complex. I'd expect to be a little bit harder if you wanted to make this into 3D printing. Is that possible? Maybe more in the future. So where do we begin? As I mentioned, if we're looking at designing any product, we want to think of everything from a different perspective if we're looking at 3D printing to other manufacturing techniques. So as a simple example, let's take a coffee cup. Some of the key areas we want to look at there is, how does it function? What's the handle shape? Does it have a handle? What's the size of the cup you want? Does it have a rounded lip? What will it look like? Form, decorations, any colors? How much will it cost? Does it design it, to manufacture it, to ship it? What materials will it be made of? Do you want it ceramic? Do you want it steel? Reliability and durability comes back from material selection. How will it be manufactured? Comes back to your design, and that depends on material and form. So all of these different product design choices are all interrelated, and we have to be thinking about how we want to manufacture it back from the start. And then the last part is the marketing strategy. What's the style of the marketing, the features, and the benefits? So as a designer, we've got a choice of all of these different tools here which we can use. We can sketch the design, we can do renderings and scale drawings, we can do 3D CAD models, physical mock-ups. Back when I was doing industrial design, I had foam sandwich boards all over the place, making models out of foam boards and clay, scale models or prototypes. These days, we can actually use 3D printing to help in all of these areas to help us get a better and more efficient product. So in reality, the product process would look something a little bit like this. Come up with an idea. You want to plan it, research it, get your inspiration. Then you want to start designing it. All of those areas that I just mentioned, function, designing for manufacture. You might want to create a prototype, whether that's a drawing or a physical model, and then you want to manufacture it. Do you want to cast it, fabricate it, forge it, maybe some other processes? Then depending on how you manufacture it, you've got to assemble it, and then last, market, ship it, and sell it. All of these things are coming into our decisions for our design. So briefly, the materials and the manufacturing are an important thing there. We need to choose what material we want to make our design from. When it comes to engineering, we've got a wide range of materials that we can choose from. We can use metals, ferrous metals, which are steel or cast iron. You can have non-ferrous metals, which are aluminium or copper or brass, or you can use plastics, ceramics, composites like carbon fiber, or natural materials like wood. So we've got a huge choice of materials there. We can actually pick our design to build our design from. If we wanted to 3D print this cup, or we wanted to 3D print something, have a look at this list. I'm just going to give you a few seconds to have a look through all of these items there. Which ones do you think you could not print with additive manufacturing? The ones in bold aren't there for a reason. I think it's just as a sitting there in the font. But all of those are materials we could print from. Which ones could we not print 3D in a 3D printer? As it stands, as far as I'm aware, off that list, these are the ones we can't currently print in 3D printing. And the reasons are they're a little bit too complex. Long fiber woven composites are a little bit complex to get the shape from. Batteries and electronic systems have concepts in them that are a little bit tricky. We can print living tissue to an extent, but we can't print live organs. So pretty much anything these days you want to print with 3D printers can be printed as long as they're not too complex. But not all materials are possible to print through a 3D printer. When you think about how a 3D printer works, which we'll come to in a little bit later, the material has to actually fit through a tiny nozzle. The most common materials that we print with are polymers or thermoplastics, ceramics, and metals. We could print our cup out of any of these. But the whole idea with additive manufacturing is it's a creative process. So don't limit your imagination to these. We could even print out of chocolate. So here's a cup that's being printed, 3D printed, making it out of a chocolate. There's some pretty crazy designs you can see out there of what we can make. So first thing is don't limit our imagination when we're designing things to traditional materials. As with any engineering design, we've got to consider the loads and the failure mechanisms when we're picking our design of materials. Will it degrade, like rope that's left outside will rot? Will it corrode? Or will it fail due to a load from fatigue or bending or torsion or something like that? You need to consider all of these failure mechanisms if you're selecting a material and when you're working through the design, because all of these choices will affect the shape and the properties that we want to make our design out of. So some of the common terms when we're talking about engineering material properties, engineering loads, we've got toughness. Can it withstand an impact load? If it's brittle, it will shatter under an impact load, which is, I suppose, the opposite of toughness. Strength, can it be squashed or stretched? And then how rigid or how stiff is it? Can it retain that shape under the original load? These are all properties of strength. Then we've also got what we want to call forming properties. So if it's ductile, it deforms in a plastic manner when it's pulled. If it's elastic, it changes shape and then returns back again. If it's plastic, it will deform under that load and will stay in that new shape. Malleability deforms plastically when squashed, and then hardness if it's resistant to scratching or indentation. So what does this have to do with our manufacturing choice? Traditional manufacturing processes typically form under one of these three categories, more or less. we want to choose the best process or a combination of these processes for our design. Additive manufacturing isn't a process we might necessarily use to decide on its own. To get the best option, we want to consider some of these other ones. So forming, or metal forming in most cases there, is shaping the objects through deforming mechanically. So we're not going to add or remove any metal or any material, we're just going to change the shape there. So the most easy one to picture is a guy hitting a hammer on a sword after it's been heated and sticking that sword in a bucket of water. That's sort of the easiest one to consider there, or to picture in your head. I've put casting in this group. While it's strictly, I suppose, adding material, it can come under the forming heading, because the reason there is I want to add some of the plastic forming. So we've got vacuum forming and injection molding as well. So I'm sort of relating all those to the same sort of principles. Subtractive manufacturing is things like turning, milling, grinding, finishing. The idea is they're all removing or subtracting material. So this is important when we think of additive manufacturing, because it's the opposite of the subtractive manufacturing. And then the last one here is we've got fabrication. So we've got cutting and bending and assembly of our parts. So welding, bolting. And then if we're thinking about 3D printing again, we want to also include adhesive bonding in that one, because that comes a little bit more relevant if we're wanting to bond parts. So how does this all fit in with additive manufacturing? All of this relates to build up into a design process, a material selection, our properties and strengths of the materials. Now we want to think about how can we make something using additive manufacturing. So according to the International Standards Organization, or the American Society for Testing Materials, their definition is that additive manufacturing is a process of joining materials to make parts from 3D model data. So we're going to do it layer upon layer. So we're going to build one layer up at a time, and that's the opposite of subtractive. So when we think back to what subtractive manufacturing was, it was our machining. So it was our drilling, reaming, boring, all of those sorts of things. So it's an opposite of that, and it's different to forming, which we're just changing the shape of. So we're adding materials layer by layer. Getting started with additive manufacturing can be daunting when you're first getting involved in it, but to get into it, it can be a lot easier than you think. So what I want to do now is just run through how do you get started in 3D printing? Where do we start in the first place? So the first choice you need to make is, will you be doing a technical design or something a little bit more artistic? So for instance, sculpting. Because we're here as part of the Institution of Mechanical Engineers, I'm going to focus more on the technical side. So I'm going to look at what we call the computer-aided design, or the CAD side of software. Here's a list of just some of the main ones that I've seen or been involved with, but there's a lot more other than these. FreeCAD and Tinkercad are some really good introductory free programs. The Tinkercad one there is one part of the Autodesk product range. Most people have probably been a little bit more familiar with AutoCAD and Inventor. They cost more money because they're used for professional use, while the Tinkercad and the FreeCAD are just free beginner type ones. If you're looking at getting into a little bit more functionality in 3D printing, the Autodesk Fusion is a really popular one. So I've got that one highlighted just because that's one of the key ones to look at. If you're a student or if it's non-commercial, you can actually use that for free. Or if you want to get the full functionality and make it part of your business, you can pay for it. In comparison to some of the other ones, it's not actually that expensive. As a competition to Autodesk, we've got SolidWorks. So SolidWorks is another really popular one. Costs a bit more money plus an ongoing license. If you want to get into some of the more specialized software, you're going to pay a lot more, like CATIA and Creo. They're really good for the specific things that they do, but not as general as the other one. The last two options I've put in there are for the coders out there. BlocksCAD's kind of like Tinkercad equivalent. It's really simple to follow, a really great starting point one, and then BlocksCAD will give you more functionality, but it's a lot more complicated. When I was at uni, I hated doing software programming, so it's not one that I've really got involved in. It depends what you like there. Interestingly, Tinkercad's actually just been starting to launch some block options as well, so I guess it's becoming more popular these days, but I suppose it depends on what your preferences are. So once we've decided on our software, what's the purpose of our design, the second choice is which software we use, build that in there. Fusion, as I said, one of the most popular, part of the Autodesk suite, but this is what we call Tinkercad. This is the free, brilliant one to start off with, to get going with. So your first step is to come up with an idea. What do you want to design? What do you want to build? So as engineers, we always get told to think outside the box. So let's just make that box. On the right side, we've got a whole list of basic shapes. They're all preloaded in there because it makes things a lot easier for this type of software. We've got letters, we can put words in, we've got objects, shapes, all sorts of different things people have designed. All you have to do is click on the shape or the object that you want, drag it into what we call the work plane, and that's us created our box or our cube. If you see the blue work plane there, that's actually the base or the print bed that our 3D printer is going to print on. So we can arrange all of our parts sitting on that base for our printer to print later on. So once we've created our fantastic red little cube there, what we want to do is export it into something that our printing software can recognize. So in this case, what we want to do is export it as an STL file. And STL stands for stereolithography, which I'll get into that in a little bit of time. These files store information about the 3D shape, and it describes the surface geometry using triangulation, so it makes it into triangles, and converts that into a 3D object so that it can get printed. So the next part you want to do once you've got your STL file is decide what you want to print it on. In this case, I'm going to use a FlashForge Finder printer that I use for these sorts of things. FlashForge has its own software built in, so in this case, it's better to use the software that it comes with. If you don't have that, you can get other different software, which gives you a lot more functionality, and you can tailor it to what you need. The Finder printer is quite a small print area there, so it's only 14 centimeters cubed, so it's 14 centimeters by 14 centimeters wide by 14 centimeters tall. So it's not actually 14 centimeters cubed, it's 14 by 14 by 14. It's quite a small work area there. So what the printing software there does is shows us that area or that volume that we can fit in our printer. We've got to make sure that our object fits within those 6 walls. So you can see that tiny little cube there fits neatly inside the box there. And then we've got to convert the format into something that our printer can understand. So we want to print that into another version or another format. So if you remember the definition of what additive manufacturing was, it was making parts layer by layer. So what the software does is it slices that model, in this case our cube, into layers. And it does lots and lots of layers so that the printer knows what to print. As I said, you can use standalone slicing software, or you can, in this case, I'm just using the one that came with the printer. So on the bottom right corner there, what I've done is I've cut my cube in half. And so you can see inside what the printer is going to print. Printing parts are generally not solid. The cost of printing a part on a 3D printer comes down to the print volume and the print time. So the more material we print, the more plastic or more metal we use, the more material cost. So what we want to do is make our strength not optimized, but have as little volume as possible. So that's why we've got all these voids or this honeycomb shape there. The software is pretty clever there. It will tell us exactly how much this is going to weigh. So this this box is only going to weigh 4 grams. I've selected the material as PLA, which is the plastic type that we're going to print this box out of. If you work out how much this is going to cost, you can go to any website. 1 kilo of PLA plastic costs us about £30, British pounds. So that works out at about 3 pence per gram. So that box, that cube's going to cost me 12 pence to print. And then if you see in the middle of the screen there, print time 16 minutes. So automatically I know it's going to take 16 minutes to print, and it's going to cost me about 12 pence in material. We can then change that design to be more complex or less complex depending on whether we want to change costs, we want to change printing. So let's look at how the printer actually works. Once we've got that model in place, we've got it ready to print, we're going to print that on a printer. So if you think about how an inkjet printer works, most people have seen inkjet printers. A signal gets sent from the PC. That signal then tells the print head on our printer to move across the paper, deposit droplets of ink onto our paper, and then the paper moves around so that we get writing or a picture. If we took that piece of paper, put that piece of paper back through the printer, had a slightly thicker ink, and we kept on running that printer and over, eventually we have tall letters or 3D shaped letters. So this is one version of how a 3D printer works in the same way. It builds up layers of plastic or material to make a height or make a 3D model of what we're wanting to print. So probably the most common or most known method and the most affordable method at the moment of 3D printing or 3D printers is what we call FDM, Fused Deposition Modeling. This is what a company called Stratasys patented many years ago. And these days, a similar version, FFF, which is Fused Filament Fabrication, which now other companies provide. So they're both the same technology, they're just one's a proprietary name and the other one's a generic name. So on the right there, top right corner, we've got a little boat that has been printed out using the FFF printing process. As I mentioned, thermoplastic plastics or thermoplastic polymers is one of the things we can print out. So this one's printed out in PLA, which is polylactic acid. It feeds from a plastic coil, like the one we saw in the black foil last screen there before. Plastic's then heated through a little printer head, in this case to about 200 or 220 degrees for my printer, which then fed through that nozzle and it prints up layer by layer, where each layer then cools and hardens into a hard plastic. As one layer is finished, the build platform moves down and then another layer prints up. So you can see there in the little drawings I've put in there, 3 sort of sequences of that boat being printed. Each layer is about 50 to 400 microns thick. Human hair is about 100 microns thick. So you can sort of get an idea of how much detail these types of printers can actually print. As I said, my printer does 14 by 14 by 14 centimeters. Pretty small, but again, it's sort of an educational type of basic printer. You can get industrial ones that are sort of more around the 1 meter cubed size. So you're not limited to just that small size. So as I mentioned, FFF printers are one of the types of printing processes. If we go back to what the standards say, there's actually 7 process categories there. FDM or FFF and SLA and SLS are the 3 most popular, but there's 7. So material extrusion is the one I've just shown you there with the FFF printers. We've also got powder bed fusion. This is using a thermal energy like a laser, which fuses powder together. And one of the most popular ones, as I mentioned, is SLS or selective laser sintering. So it's fusing layers of powder with that laser. One of the other most popular ones is what we call vat polymerization. That uses a vat of liquid photopolymer resin, so a vat of a resin, and it uses a light, like a UV light, to cure the model layer by layer. So I suppose this takes us back to the question on the first screen that we had there: where and when was the first 3D printer designed and developed? In 1981, there was a guy named Hideo Kodama. He came up with the idea for vat polymerization. So that number 3 on that list there. And in 1984, an American person named Chuck Hull designed and created the actual first 3D printer, which was a stereolithography printer, an SLA one. But 3 weeks before he filed the patent, a French trio of researchers registered a patent for a similar process. So 3 weeks earlier, they actually got in and patented a similar process first. They didn't see any value in it after working on it for a while, so they abandoned that idea, and in the end, Hull ended up being able to copyright the term stereolithography. So who was the first person? Was it Kodama? Was it Hull? Was it the French people? I suppose technically speaking, the French trio patented it first, but the American guy was the first one to do it. Interestingly, he later went on to develop a company called Stratasys. So I suppose the French people didn't actually make the right call there in deciding that there wasn't much value in it, because if you've seen who Stratasys are, they're making quite a success out of 3D industry. So the fourth one, material jetting, that's using droplets to build onto a platform, so things called multi-jet or polyjet. This one, binder jetting, using a powder and a liquid binder. We've got sheet lamination, where we're using ultrasonic welding to bind the sheets together. And the last one there, which is getting pretty popular in manufacturing industries, and I'm going to show you an example of this one shortly, is what we call directed energy deposition. So it's using a laser and the powder to be fused together. So there's a huge range of printing processes. So the first one, material extrusion, FFF, is the most widely known, the ones that you're making little plastic things out of. But depending on what you want to print, what properties you want, you need to print the right material and the right processes. So let's print something. So here's what I said was before, the Flash Forge Finder, which used for a while now. It's an FFF printer, so it's a material extrusion printer. What I'm going to do first here is just to print off a little mobile phone stand. So you preheat the plastic to about 220 degrees in this case. It's preloaded into the printer for this one, so you just print go. The bed then moves up to the print head, so you can see the nozzle touching the print bed just above the G there. And it's starting to deposit the base layer of the print material, or the PLA plastic. If you look from the top view, this is it having printed a few layers. The narrow part in the middle is actually the phone holder on its side, starting to build up some height. The flatter, wider part that's underneath it is what we call the raft. The raft is there to provide a bit of stability to something that's thin and a little bit less unstable, and to help us get some adhesion to that print bed. In this printer, the print bed isn't actually heated because we're only using PLA plastic. So we want to get as much adhesion and as much stability. So it's got a raft, what we call a raft at the bottom, to add it. So that black print nozzle at the top there is moving around, laying down our layer by layer to build it up. Back to the front view again, and you can see there we're about halfway through the printing process. The phone holder is starting to get taller. It's on its side there, so it's building up layer by layer. The print bed is moving down as each layer is printed. We've now got our last layer. It's almost finished printing. Once complete, the print bed moves away, the printer head moves away, and we've got our finished plastic model cooling down and hardening. For this one, we can actually remove that print bed, that base. It slides out to give us a better access. You can see the sides of this printer, it's not enclosed, So it allows you to get your hands in and get a bit more access, so we can take it out and away from our printer. See there, it's still sitting on our print bed. The raft just snaps off the base. It's just got a very thin layer, enough to hold it together, but not enough to join it. So it just snaps off, and you throw that away, and then you're left with the holder itself. So on the left there is our holder on the side, sitting before I've removed it from the print bed. And then the next two photos are mobile phone sitting neatly in our folder, all printed. There's no post-processing for this other than taking off our base. What I've actually done is I've put the video footage, it's only a minute or two of video footage, onto my YouTube channel there. So if you want to have a look at the actual printing video footage of this, you can go to the Project Engineering Management website, go to the news page, and there's a YouTube link or an actual article there. So you can watch that in printing process. For this one, I've just used it photo form just so we can get a bit of an idea. So as engineers, obviously we're known as our romantics. So what I've decided is to whip up a diamond ring just as something slightly different there. Clearly we're also cheap as well, but I thought I'd just design this up just to see how it printed off. So the one on the left there is a model drawn in Tinkercad, sitting on the print bed, just up on its end, and the one on the right there is printed out a complete once I've taken the base off and some of the supports off. You can see there the one on the left, I've just used that exactly as it was from Tinkercad, so it's actually not very curved. The finish isn't very good, but I left it like that just to see what it would look like. And you can see on the right there, it's printed out pretty much exactly like it's shown there, with sort of the jagged edges a bit. Not perfect, but not too bad for just a default one there. So this is the whole thing. Come up with an idea, load in your shapes, manipulate your shapes, convert them to an STL file, drop them into your program or your slicing printer software, print them up. This one took me probably 5 minutes to design up. It took about 25 minutes to print. So it can be pretty simple there. And again, if you want to see the footage of that one printing, that's on the channel as well. So there's a photo of it just printing with the diamond part printing on the bed first. Obviously, printing little gimmicks isn't the main benefit as engineers. It can be great fun, it can be great as backup anniversary presents, obviously, but it's also used in engineering. Engineering is the main benefit that we want to look at here. So this is a study that a company called the AFRC, the Advanced Forming Research Centre, did, which is part of Strathclyde University in Glasgow, where we've got a gear and it's made from a material called EN25, which has got nickel and chromium and molybdenum. It's very hard, high tensile, and this is where the understanding of the material properties and manufacturing comes into it. How would you repair this? In traditional formats, we could cast it, we could forge it, we could fabricate it. It's going to cost us a lot of money to make that. It's probably about 400 or 500 millimeters diameter. So the option that they came up with is what we call a hybrid version. So it's combining the last option I showed you there, laser metal deposition, and combining that with CNC machining. The deposition part took 9 minutes and the machining took 6 minutes. So within about 15 minutes, our whole ear tooth has been refurbished. So again, we'll go through first one. What we want to do is machine it. Use a CNC machine. The top of that gear tooth, we're going to machine it off, get rid of the worn part of that. Once we've machined it off, we then want to build up the material again with print material. So we're going to use laser metal deposition to build up our gear tooth again. So on the right there, we've got our finished tooth rebuilt using 3D printing. We then need to use subtractive machining again to rough machine it. And then we want to finish machine it, make it back into the original or the properties that we need it to be. So you can see there from just one simple example there, we've saved a huge amount of money, huge amount of time. We've got to retain the asset so it's environmentally friendly, and we've just done one single machine setup, one manufacturing program where it's going to machine it and weld it and then machine it back together again. This is where the real benefits are starting to come through. Other benefits is we can make as complex as we want almost, and parts are consistent when we're 3D printing. One part to make costs as much as 100 parts or as 1,000 parts. As compared to conventional production or traditional manufacturing, the first ones are going to cost us a lot of money because we have to spend thousands of pounds on the tooling. The more volume we make, the cheaper the parts eventually become. The disadvantages are it can be slow. It takes a lot of time to print lots of parts. And getting design approval for 3D printing is a little bit more complex as well. Qualifying and validating those designs can be a bit more of a challenge. So stick with subtractive methods if we've got machine pieces or simple extrusions, or we've already got the tools made or something existing there. Consider 3D printing though, if we need to make a tooling to start with. We can make a tool with our 3D printer and then use traditional manufacturing methods. Or if we want to use prototype to make one or two small parts as prototypes, or we've got low volumes, low lead time, short lead times. Or if we just want to have some fun, you know, why can't we just make things just to design and experiment and have fun and make our own parts up? So what does the future bring for 3D printing? At the moment, we've got sort of 4 key areas as I see it. We've got product development. We can make those prototypes, those one-offs, small volume things. We can use it to make concepts, show form, rather than using the old-fashioned foam boards and clay models. We can use it to make molds and jigs and quality assurance checks. And then we've got marketing. We can actually make it to show hands-on physical form things so that people can actually get an idea of where or what they feel like, what they look like. 2 articles which have been recently in the Professional Engineering magazine from IMechE, PE magazine. So those of you who are members get this regularly through printed or in the emails. Not too long ago, so it was 2016, is an example of a resin 3D printed part. And they can print pretty much any shape or size, complex ones. This one's using a ceramic component. So once the ceramic model has been made, you fire it, which makes it very high strength and very high density. This one can actually withstand temperatures of over 1700 degrees. So it's 10 times the strength of similar materials. Another hot topic at the moment, the coronavirus. So ventilators and breathing equipment are becoming more in demand. One thing there that's becoming more recognized there is the ventilator challenge, where the government are wanting rapidly manufactured ventilator systems. We can use augmented reality, so our 3D AR glasses, like Google glasses, in this case it's Microsoft HoloLens, capture the video. Then we can use that video to train workers remotely, the correct steps, lead times, we're preventing transmission. So we're now starting to use other technologies with manufacturing techniques. We can then use 3D printing to print the valves. We can print hundreds of valves a day. This one's an example of converting a snorkel mask into a ventilator. Once we've come up with our design of our snorkel, we could then make it out of injection molding for faster manufacturing. So make the prototype in 3D printed and then use it injection molded to get cheaper, higher volume parts. So most people, I think, see 3D printers in the general public, I suppose, as plastic and gimmicky type of things, like the phone holder that I made or that ring there. You know, great to make those, sell small parts and that. But for manufacturers, I think the future means that we're going to be able to offer more customizable parts. more customizable products. It brings more affordable off-the-shelf mass production, and then we can combine that with those one-off bespoke items to make mass production. So what it's going to do is it's going to start lowering the cost of our parts. We're going to be able to choose the best manufacturing process for the thing we want to use it for. It's going to lower the cost of labor to manufacturing, so that maybe some of these manufacturing can be brought back to other countries where traditionally they couldn't afford to do it because the cost of labor is higher. And then 3D printing is also going to make it increase the productivity. You're going to possibly need less people, so it's going to reduce lower production costs, lower prices for consumers, and more demand. So it's going to give us far more versatility, far more options of what we want to do, making the most efficient, the most effective design that we can come up with. So hopefully you've learned a little bit about some of the advantages of using additive manufacturing. Obviously, as a designer, it's great to play around with these little home printers or little small type of FFF printers. Print your own ones, absolutely, that's great, and you'll learn a huge amount by just playing around with those yourself. But the main benefits I see in the future are coming with industry, bringing that in with manufacturing. Don't think of 3D printing as a standalone process. Use it to incorporate it with existing traditional processes. So, as I said, those videos are all available on the website there, which you'll see on the next page in a minute. If you want to know a little bit more about 3D printing, so how does 3D printing work in a lot more detail, what are the other processes, the 7 processes there, what are the costs, what are the lead times, software. The IMechE, we're running a course, a virtual classroom course here on a guide to additive manufacturing. So a lot more in-depth and a lot more related to case studies and showing how that will work in the industry. We've got one there coming up towards the end of May there. It's on the IMechE website. I think now, so I'll hand it back to Rob there to take any questions anyone might have. You there, Rob?
Yeah, thank you, Matthew.
Yep.
Rach, can I have the control back? You can change the slides. Thank you very much. And then I'm now the presenter. Well, just before we hit on the questions, as Matthew briefly came on there, we have, in these circumstances at the moment, we have a number of free webinars. Obviously, you attend this one, virtual classrooms, e-learning collection, qualification, diagnostic tools that can be delivered virtually or online. So please just go to the IMechE, our website, our training website. Click on the e-learning portal and you can see what we have to offer. Questions. There are a number of questions around recommendations of printers and costs. Matthew, I don't know if you want to have a quick chat or have divulge some information about that.
Yeah, so I suppose it depends on, the first thing you need to do is choose which what you're wanting to print. If it's industrial or if it's in the engineering industry there, the printers can be really expensive. So if we start with some of the hobbyist type ones or the little ones that we can use ourselves, as I said, the one I've got there, which is a Flash Forge Finder, it's very small, very easy to get set up. I think they're selling those at the moment for under £300 British pounds. So pretty economical there to use. There's another sort of, so the other ones that are popular, Prusa, PRUSA, they're from Poland. They have quite a lot of introductory type level ones and also a lot of more sophisticated PLA type of ones there, starting with I think about $200 or $250 US up to hundreds in the thousands of pounds. One of the ones I see a lot of the time is Creality, Creality. Again, they start at hundreds of pounds, going up to a lot more. If you want to get into some of the more sophisticated ones where you've got print bed control, temperature control, they're enclosed. You've got MakerBot, Ultimaker, and then I mentioned Stratasys, which are a lot more expensive. So all of those ones, you know, the introductory type of PLA, FFF type ones can start at a couple of £100. I definitely wouldn't recommend spending only $100 or $200 on a printer because they're going to be pretty difficult to play around with and get good quality. I'd probably start in a couple of £100 as a minimum, £100 as a minimum, up to, you know, a few £1,000, and then the industrial ones are sort of £5,000 plus.
Thank you, Matthew. Question from George here. So it seems pretty slow, but I understand these are home devices. How quickly can a complex crankshaft be made for a real engine? And how quickly can sample parts be produced in industry, i.e. mass produced?
Okay, so what was the first bit? How quickly?
So how quickly can a complex crankshaft be made for a real engine?
Oh, right, okay.
Be produced in industry, i.e. mass produced?
It's a good question. So a crankshaft like that, the metal process, I guess, is going to take longer than just using the plastic there. It's going to be hours, and when I say hours, like overnight minimum. So normally what you would do is you would set your printer to print. A lot of people, what they'll do is they'll just have their printer running 24 hours, 7 days a week, and keep on printing things. So the crankshaft there is going to take, geez, I'm going to guess sort of 10 or 20 hours maybe to print. And the thing you're going to be paying for is the material. So what's the volume of material is going to dictate how much it's going to cost. If you don't have your own printer, you can actually outsource the printing process. So you could design it yourself. You could then outsource it, send the design off to someone who will then print it for you. They'll do a design check as well, and then they'll send it back to you printed once it's done. Obviously, they're going to charge a markup, but that might come back in about a week's time, something like that, from a remote source.
Quick question here. What's the difference between FFF and FDM?
Yep, so they're the same thing. FDM was the name of the process that was patented by Stratasys from that guy, Chuck Hull. They coined the term FDM. And then the patent actually ran out, I think it was in about 2003 or something like that. And that made that technology open to everyone else, and then everyone else just calls it FFF. So they're the same thing, it's just one's by Stratasys.
So, next one is, excuse me. Can you print buildings with concrete?
Can you print buildings?
Yeah.
Yes, so recently I've seen houses being built and buildings being built. So I suppose the easiest way to visualize that is if you've got a tube of toothpaste and you squeeze that toothpaste and then you build up the next layer of toothpaste, you'll have effectively a 3D printed toothpaste layer. That's kind of what I've seen as the houses and building that they're building. They're using some sort of semi-solid concrete-y type material to build layers up of walls. The houses I've seen have kind of show that curved edges like it would be if it was a tube of toothpaste being squirted, and then they just insert their windows into it. I think they've built a house for about £3,000, £3,000 in some other countries to get cheap, affordable housing. So, you know, very rough and ready, but I think the technology is actually increasing to get to that point.
What else have we got here? I think we've covered a lot of these. See what new ones have come in. Hold it. Yeah, there we go. how much printing is used in aerospace industry, and is it effective?
So aerospace is probably one of the main areas that it's increasing in use. If you think about aerospace and the risk involved in parts, I suppose it's one of the areas you expect it not to be used because the risk of failure is higher. But the amount of research and the amount of money that's being spent in the aerospace industry means that they're doing a lot of validation, a lot of checks, and a lot of analysis. So it's one of the most widely used areas, the aerospace.
So, quite a specific question here. I would like to know regarding customization of designs in Thingiverse, I think it is.
Yep.
It seems that the option is not working well since a few weeks. Can you suggest other software?
Yeah, so Thingiverse, for those of you who don't know what Thingiverse is, it's sort of an open source repository of 3D models that people have printed and designed. So they put the STL files up there, and then you can go and download it and print it yourself. The problem with that is that it's kind of, I guess, like Wikipedia. It's just people are designing up themselves and available for print. There's a lot of errors and a lot of failures and things, so you've got to be careful. There's another one called YEGGI, YEGGI, which is also a popular one. I'm just trying to think of what other ones I've used. There's IMechE, I think, is another one. IMechE. So, and then I think it's IMechE, something like myminifactory.com might be another one as well.
In a sort of addendum to that, there's also been a number of questions about the difference between Mac and PC, and I think there's a general consensus that the software doesn't work particularly well with Mac. Can you recommend anything that works with Mac well?
I don't have a Mac computer, so I've actually never tried it with a Mac. I'm pretty sure things like Fusion and that have Mac versions. So I would be surprised if, some of those bigger type of softwares like Autodesk and SolidWorks and that probably would have Mac. So Fusion 360, I guess, would be the recommendation, but it's a little bit more complex than using some of the simple softwares.
Yeah, another one here. How do we get desired material properties from metal printing?
On which printing?
Printing metal.
Metal printing.
Mm-hmm.
How do we get the desired properties? I suppose it comes down to, part of it is the material you're selecting and the controls on the printing process. So if you think about the basic plastic printing, the temperature is going to affect how well the plastic extrudes. The speed with the printer, what speed the print head runs with, depends on how much it deposits and then how much it fuses with each layer. So the same way with most manufacturing processes, you have to make things and then do trials or experiments and tests on them. So decide on the material properties you want, look at those fusing abilities and the production abilities, and then do your tests to try to validate those tests. Would be, I suppose, the simple answer.
We've got time for a couple more before the half hour.
Yep.
If we're using 3D printed parts for prototyping or for actual use, is there any way to do stress analysis considering the manufacturing method of building up in layers?
So one of the areas where they're developing in the software is in software stress analysis. In your 3D printer part, the strongest, or I suppose the weakest orientation that you've got is because it's got layer by layer. So again, if you think about the plastic one, when you're building up layers of the plastic, you're going to have weaker in the one direction where you're laying the layers, and that will break off less than the longer threaded direction of the plastic. So you have to make sure you orientate the printing part in that direction that you want the highest stress. So you've still got to put in things like gussets on your bends or on your right angle joints, putting curves, to reduce stress raises and those things like that. But the software isn't as developed to analyze that stress analysis as a normal manufacturing part. So it's getting there from what I've seen, but I don't think it's as good yet to analyze the stress. And again, I think some of the highly complex programs might do it, but in smaller ones, you probably want to be careful of.
Yep. Final question then, and apologies for not answering all the ones, we're quite close to time. Do you see 3D printing, additive manufacturing being used to reduce waste of exotic materials, i.e. titanium and so on?
Absolutely. One of the main benefits of 3D printing is that it's additive and not subtractive. So if you think of how you would make something traditionally using machining, you start off with a block and then you carve out the bits you don't want, and then you're left with the material that you do want. All of that stuff you've machined off has to go to waste. You may be able to recycle it, or you may be able to dispose of it. 3D printing has a very small amount of waste if you design it efficiently. So you're only printing the part that you want to use, plus some supports or internal features and things to add to supports there. So there's far less waste when you're using 3D printing with any material. So in broad terms, it is more environmentally friendly for the waste part, yes.
Excellent. Thank you, Matthew. And thank you for all you guys attending. Excellent questions from you all, and I hope you enjoyed the content from Matthew. Okay, thank you very much, and that'll be all from us.
Thanks, Rob. Thanks, everybody.